October 7, 2025, 14:32 UTC, the European Space Agency breaks 4 days of unprecedented silence with a simple press release titled "ExoMars Images Capture Interstellar Visitor." Attached are 3 images, fuzzy white dots against star fields, exactly what you'd expect from a routine comet observation. Normal, unremarkable, safe. But here's what makes this release the most disturbing development in the entire 3IAT-LS story. If these images are so normal, so routine, so perfectly explainable that ESA felt comfortable publishing them immediately, why are NASA, China, and the UAE still maintaining complete radio silence about their observations from the same flyby event? Think about what we're being asked to believe. 7 spacecraft observed the same object at the same time from different positions around Mars. ESA's instruments, admittedly the least powerful of the group, captured images showing a typical comet with a typical coma. Nothing unusual, nothing requiring extensive analysis, nothing that couldn't be published within days of observation. Meanwhile, NASA's Mars Reconnaissance Orbiter, with its high-rise camera capable of resolving objects down to 30 centimeters. Silence. China's Tianwen-1 orbiter, which has published over 14,000 images in 4 years of operation. Complete silence. The UAE's Hope orbiter with its advanced spectrometers. Not a single data point released. This isn't how space agencies behave. This isn't how scientific competition works. When you have data that confirms expected results, you publish it. You demonstrate your capabilities. You claim your piece of the discovery. You don't coordinate multinational silence while your European colleagues share harmless fuzzy dots with the world. Unless, of course, your data doesn't show harmless fuzzy dots. The mathematics of this situation are uncomfortable. ESA operates 3 spacecraft at Mars: Mars Express, launched in 2003, and the ExoMars Trace Gas Orbiter, a joint mission with Russia launched in 2016. Both carry cameras and spectrometers, but neither represents the cutting edge of planetary observation technology. Mars Express's high-resolution stereo camera was state-of-the-art 20 years ago. ExoMars TGO's CASIS camera is capable, but designed primarily for surface imaging, not deep space astronomy. Compare this to NASA's Arsenal. Mars Reconnaissance Orbiter carries HiRISE, the most powerful camera ever sent to another planet. At 3I, at LS closest approach distance of 29 million kilometers, HiRISE should have achieved a resolution of approximately 30 kilometers per pixel. That might not sound impressive until you realize it's the highest resolution image of an interstellar object ever captured in human history. Higher resolution than Hubble's observations of Oumuamua. Higher resolution than any ground-based telescope could achieve for Borisov. If HiRISE captured a normal comet, NASA would have published those images immediately. They would have celebrated capturing the most detailed view of an interstellar visitor ever obtained. They would have used it to demonstrate American technological supremacy in space exploration. The fact that they haven't, the fact that they're maintaining silence while ESA publishes routine observations, suggests they didn't capture a normal comet. China's behavior is even more telling. The China National Space Administration views every space achievement as an opportunity to demonstrate national prestige. When Tianwen-1 entered Mars orbit in February 2021, CNSA released images within hours. When the Zhurong rover landed 3 months later, high-resolution surface photos appeared immediately. In 4 years of Mars operations, CNSA has maintained a relentless pace of public releases, showing everything from dust devils to seasonal changes in the polar ice caps. For 3IAT-LS, nothing. Not one image. Not one press statement. Not even acknowledgement that they attempted observations. This violates every pattern CNSA has established. If their cameras captured routine comet imagery, they would have published it immediately, probably beating ESA to the punch as a matter of national pride. Their silence indicates they captured something that requires careful consideration before public release. The UAE's Hope orbiter adds another layer to this puzzle. The Emirates Mars mission has been remarkably transparent throughout its operation, sharing data freely with the international scientific community. Hope carries the Emirates Mars infrared spectrometer, perfectly capable of analyzing the chemical composition of a passing comet. If that analysis showed typical comet chemistry, water ice, carbon dioxide, trace organics, the UAE would have no reason to withhold the results. Their silence suggests the spectroscopic data revealed something unexpected. So we have a situation where the space agency with the least capable instruments publishes normal-looking images within days, while the agencies with the most advanced cameras and spectrometers maintain coordinated silence. This isn't scientific caution. This is information management. ESA's release comes with carefully crafted language that reveals as much through what it doesn't say as what it does. The images show a slightly fuzzy white dot moving against background stars. The comet displays a coma, measuring a few thousand kilometers across. These observations are described as extraordinarily difficult due to the object being 10,000 to 100,000 times fainter than the instrument's usual target. Notice what's missing from this description. No mention of unusual properties. No discussion of unexpected chemical signatures. No reference to anomalous behavior. Just technical challenges overcome through extended exposures. It's the most sanitized possible description of what could be the most significant astronomical observation in human history. But here's where ESA's careful language becomes revealing. They admit uncertainty about spectroscopic results, stating it's uncertain whether the coma and tail were bright enough for spectral characterization. This is curious phrasing. Either you obtained spectra or you didn't. Either the instruments detected chemical signatures or they failed to do so. Uncertain suggests they have data, but are unsure about releasing it. The timing of ESA's release carries strategic implications. By publishing their observations first, they establish a baseline of normalcy. They're saying, here's what we saw, here's what we're comfortable sharing, here's the standard of transparency we expect from our colleagues. It creates public pressure on NASA, China, and the UAE to match this level of openness. It's a diplomatic move disguised as scientific publication. ESA is forcing other agencies to either release their data or explain why they can't. And given that ESA's less capable instruments captured publishable results, the continued silence from agencies with superior technology becomes increasingly conspicuous. The release also comes at a strategically significant moment. We're now 3 weeks from Perihelion, when 3I at LS disappears behind the Sun. Once that happens, all Earth-based observation becomes impossible for several weeks. If other agencies plan to release data that contradicts ESA's normal comet narrative, they need to do it before the object becomes unobservable. ESA's early release starts a countdown clock for disclosure. There's another possibility, one that makes this release even more intriguing. ESA might be deliberately showing us the least interesting data they have. The fuzzy dots and routine observations might represent the most mundane moments of their observation period, carefully selected to appear normal while more significant data remains classified. It's a way of technically fulfilling transparency obligations while withholding the truly significant discoveries. Consider the technical details ESA provided. 5-second exposures were required to capture the comet at all. CASIS, designed for bright Martian surface features, was pushed to its absolute limits detecting this faint object. Yet somehow, despite these extreme technical challenges, they managed to create a time-lapse animation showing the comet's motion across multiple observation sessions. This raises questions about what ESA isn't showing us. If they could capture motion across multiple sessions, they have more data than the 3 static images released. Where are the intermediate frames? Where are the detailed close-ups from the moments of best atmospheric conditions? Where are the images that didn't make it into the official release? The story ESA tells is one of technical triumph over challenging conditions. Their instruments, designed for surface geology, successfully adapted to deep space astronomy. Their teams overcame significant obstacles to capture valuable scientific data. It's a narrative of competence and capability, designed to enhance ESA's reputation in the international space community. But viewed in the context of the broader 3I at LS mystery, ESA's release feels like misdirection. They're showing us a magic trick with one hand while keeping the other hand carefully hidden. The images are real, the observations are genuine, but they may not represent the complete picture of what ESA's instruments detected during those crucial days in October. As the silence from other agencies continues, as the countdown to Perihelion accelerates, ESA's strategic release becomes the opening move in what may be the most significant disclosure event in astronomical history. They've established their position, created public expectations, and forced their international colleagues into an increasingly untenable position of secrecy. The question now isn't whether other agencies will release their data. The question is what that data will show when they finally have no choice but to share it with the world. Let's examine what the European Space Agency actually put before the world on October 7th, because understanding exactly what they showed us, and more importantly, what they didn't show us, reveals the deeper strategy at work here. The primary release consists of 3 images captured by the CASIS camera aboard the ExoMars Trace Gas Orbiter. CASIS stands for Color and Stereo Surface Imaging System, and that name tells you everything about why these images are both remarkable and suspicious. This instrument was designed to photograph the Martian surface in high resolution and create 3-dimensional maps of geological features. It was never intended for deep space astronomy. The first image, taken on October 1st, shows what ESA describes as a slightly fuzzy white dot near the center of the frame. The object appears against a field of background stars, clearly distinguishable but without obvious detail. The image metadata indicates a 5-second exposure time, extraordinarily long for an instrument designed to capture planetary surfaces in milliseconds. This alone suggests CASIS was operating far outside its design parameters. The second image, captured on October 3rd during closest approach, shows the same white dot, now slightly brighter and marginally larger. The improvement in visibility is consistent with the reduced distance, from approximately 31 million kilometers on October 1st to 29 million kilometers at closest approach. Basic physics, basic astronomy, exactly what you'd expect to see. The third image from October 7th shows the comet appearing dimmer and smaller as it moves away from Mars, continuing its trajectory toward the inner solar system. Again, perfectly consistent with natural comet behavior as observed from an increasing distance. Compiled together, these 3 images create a simple animation showing 3I at LS motion across the star field over a period of 6 days. The object moves smoothly from upper left to lower right in the frame, maintaining consistent brightness characteristics throughout the sequence. It's a textbook demonstration of celestial mechanics, orbital motion rendered visible through patient astronomical observation. This is what ESA showed us. A normal comet doing normal comet things, captured through technical skill and persistence by instruments not designed for this type of observation. The narrative is professional competence overcoming technical challenges to achieve valuable scientific results. But let's examine what they didn't show us, because the omissions are as revealing as the inclusions. ESA stated that Mars Express also attempted to observe 3I at LS using its high-resolution stereo camera, but the comet has not yet revealed itself in those images. They explain this failure as a result of shorter exposure times, limited to half a second compared to CASIS's 5-second capability. The implication is that Mars Express simply couldn't detect the faint object with its more limited exposure duration. This explanation deserves scrutiny. Mars Express has been operational since 2003, 22 years of successful imaging operations. The high-resolution stereo camera has captured thousands of detailed images of Mars, many under challenging lighting conditions. While it's true that the camera has exposure limitations, the suggestion that it completely failed to detect an object successfully imaged by CASIS seems convenient. More suspicious is ESA's statement that they're working to combine multiple Mars Express images, stacking them together to bring out the faint comet signal. This is standard astronomical technique. When an object is too dim to detect in a single exposure, you take many images and add them together. The signal accumulates while noise averages out, revealing features invisible in individual frames. The question is, why announce this technique if they haven't completed it yet? Why mention ongoing analysis of Mars Express data in a press release focused on successful CASIS observations? The most logical answer is that Mars Express did capture something significant enough that ESA wants to prepare the public for additional revelations while maintaining plausible deniability about what those revelations might contain. Then there's the spectroscopy issue, which ESA handles with masterful ambiguity. They deployed 3 different spectrometers, Omega and Spicum, on Mars Express, and Nomad on ExoMars TGO. All 3 instruments were aimed at 3I at LS during the flyby period. All 3 are capable of analyzing the chemical composition of cometary gas clouds. ESA's statement: at this point it is uncertain whether the Coma and tail were bright enough for spectral characterization. This is not how spectrometers work. Either they detect spectral lines or they don't. Either you obtain chemical composition data, or you fail to obtain it. Uncertain suggests they have data, but are unsure about interpreting or releasing it. Consider the implications if ESA's spectrometers successfully analyzed 3I at LS chemical composition. They would know definitively whether the object shows the nickel without iron signature detected by ground-based telescopes. They would know if the carbon dioxide dominance holds up under closer observation. They would know if there are unusual chemical signatures that don't fit natural comet models. If this spectroscopic data confirmed normal comet chemistry, ESA would have published it immediately. Successful chemical analysis of an interstellar object would be a significant scientific achievement, worthy of major press coverage and academic publication. The fact that they described the results as uncertain suggests the data either failed to confirm normal chemistry or revealed something unexpected. ESA's timeline for future analysis adds another layer of intrigue. They state that scientists will continue analyzing data over the next weeks and months. This is not the timeline for routine comet observations. When you capture images of a typical comet, preliminary analysis happens within days. You measure brightness, estimate size, track motion, check for unusual features. Basic characterization doesn't require months of careful study. Extended analysis timelines are reserved for anomalous observations, unexpected results, data that doesn't fit established models. ESA's projection of weeks and months suggests they're dealing with something that requires careful interpretation, probably consultation with international colleagues, possibly coordination with other agencies holding similar data. The language throughout ESA's release maintains careful scientific neutrality, but certain word choices hint at underlying complexity. Colin Wilson, ESA's project scientist for Mars Express and ExoMars, described the observations as responses to unexpected situations. The word unexpected appears twice in the official statements, once in reference to spacecraft responses and once regarding observational challenges. What about this observation was unexpected? The trajectory of 3I at LS has been precisely calculated for months. Its closest approach to Mars was predicted with high accuracy. The timing was known well in advance. Multiple spacecraft were deliberately positioned to observe the flyby. Nothing about the basic logistics should have been unexpected. The unexpected elements must relate to the object itself, to what the instruments detected when they examined 3I at LS at close range. Properties that weren't anticipated based on earlier observations, behavior that doesn't match comet models, signatures that require careful analysis before public discussion. ESA's decision to release preliminary results while describing ongoing analysis creates an interesting dynamic. They've satisfied immediate public interest with visible evidence of successful observations while reserving the right to make additional revelations as analysis continues. It's a controlled disclosure strategy that maintains scientific credibility while keeping options open for future announcements. The images themselves, while appearing routine, contain details that merit closer examination. The slightly fuzzy white dot description might be technically accurate, but it doesn't capture the full complexity of what's visible in the actual image data. Digital enhancement techniques can reveal structures, asymmetries, or features not obvious in standard processing. Independent analysis of ESA's released images might uncover details that weren't emphasized in the official interpretation. The timing of image capture also raises questions. Why October 1st, 3rd and 7th? Why not daily observations throughout the flyby period? CASIS has sufficient operational flexibility to capture images on any day when Mars Express's orbit provides appropriate geometry. The gaps between observation dates suggest either operational constraints we're not being told about or selective release of specific images from a larger dataset. ESA's coordination with other agencies remains murky. While they operate independently, major astronomical observations often involve informal communication between space agencies, sharing of preliminary results, coordination of observation strategies. ESA's decision to publish, while others remain silent, either represents complete independence or a coordinated strategy where ESA plays the role of initial disclosure, while others prepare more detailed revelations. The technical achievement ESA claims is genuinely impressive, adapting surface imaging instruments for deep space astronomy, achieving successful observations despite challenging target characteristics, creating time-lapse animations from multiple observation sessions. This represents significant operational skill and demonstrates the versatility of Mars-based platforms for broader astronomical research. But impressive technical achievements can also serve as cover for strategic information management. By emphasizing the challenges overcome and the technical skill required, ESA creates a narrative that explains why their results might differ from observations made by other agencies with different instruments and different operational constraints. What ESA showed us is a masterpiece of controlled disclosure. Enough information to satisfy immediate curiosity, enough technical detail to demonstrate competence, enough ambiguity to keep options open for future revelations. They've established their position in the 3I at LS story while carefully avoiding commitments about what deeper analysis might reveal. As we move closer to Perihelion, as pressure builds on other agencies to match ESA's transparency, these preliminary results become the baseline against which all future revelations will be measured. ESA has set the standard for what constitutes acceptable public disclosure about 3I at LS observations. Whether that standard represents the complete truth or careful preparation for more significant revelations remains to be seen. Here's where ESA's story begins to unravel, and it's not through conspiracy theories or speculation. It's through basic physics and engineering limitations that make their claimed observations technically problematic. The Cassis camera aboard ExoMars TGO was designed with very specific parameters. Its field of view is 1.35 degrees wide, optimized for capturing detailed strips of the Martian surface from orbital altitudes between 400 and 500 kilometers. The spatial resolution at typical operating distance is 4.6 meters per pixel, meaning it can distinguish features on Mars the size of a small building. Now, let's talk about what happens when you point this surface imaging camera at an object 29 million kilometers away. At that distance, Cassis's spatial resolution becomes approximately 30 kilometers per pixel. This means that any feature smaller than 30 kilometers across would be unresolvable, appearing as a single pixel or less. For comparison, most comet nuclei range from 1 to 10 kilometers in diameter. Even the largest known comet nuclei, like Hale-Bopp at roughly 40 kilometers, would appear as barely more than a single pixel in Cassis imagery at 3I at LS flyby distance. But here's the real problem. ESA claims to have imaged not just the nucleus but the coma, the cloud of gas and dust surrounding the nucleus. They describe this coma as measuring a few thousand kilometers across. At Cassis's resolution at 29 million kilometers, a coma several thousand kilometers wide should be clearly visible, extending across dozens of pixels in the image. Yet what ESA released shows only a slightly fuzzy white dot. If the coma truly measures several thousand kilometers across, it should appear as a distinct extended structure in the Cassis images, not a point source. The discrepancy between the claimed coma size and the actual appearance in the images suggests either the measurements are incorrect, or the images have been processed in ways that obscure the comet's extended structure. There's another technical issue: exposure time versus spacecraft motion. Cassis required 5-second exposures to detect 3I at LS, extraordinarily long for an instrument designed for rapid surface mapping. During those 5 seconds, ExoMars TGO continues moving in its orbit around Mars at approximately 3.4 kilometers per second. Over a 5-second exposure, the spacecraft travels roughly 17 kilometers. This orbital motion should create image smearing, blurring any point sources across multiple pixels in the direction of spacecraft movement. Yet ESA's images show 3I at LS as a relatively sharp point source, not a streaked blur. This suggests either the images have been extensively processed to remove motion blur, or the exposure methodology involved techniques not described in the official release. The background star field provides another technical puzzle. Cassis images show background stars as sharp points of light, clearly resolved and suitable for astrometric position measurement. But if 5-second exposures were required to detect 3I at LS, those same exposures should have significantly overexposed the background stars, causing them to bloom and saturate the detector pixels. Stars that appear properly exposed in 5-second Cassis images should be much brighter than the faint comet target. The fact that both the comet and background stars appear correctly exposed in the same image suggests either multiple exposure techniques were combined, or the actual observational parameters differ from what ESA publicly described. The spectroscopy claims present even greater technical challenges. ESA deployed 3 spectrometers: Omega, SpyCam, and Nomad. All 3 are sophisticated instruments capable of detecting trace gases in the Martian atmosphere at concentrations measured in parts per billion. But detecting spectral signatures from a comet 29 million kilometers away requires entirely different operational parameters. Nomad, the most capable of the 3 instruments for trace gas detection, has a field of view of approximately 0.17 degrees. At 3i at LS distance, this corresponds to a spatial coverage of about 90,000 kilometers. If the comet's Coma truly measures only a few thousand kilometers as ESA claims, it would occupy less than 5% of NOMAD's field of view, dramatically reducing signal strength and making spectroscopic detection extremely challenging. For successful spectroscopy of such a faint, small target, you need precise pointing accuracy, stable tracking throughout extended exposures, and careful background subtraction to separate the comet's spectral signatures from instrumental noise and scattered sunlight. ESA's description of the observations as extraordinarily difficult understates the technical challenges involved. Yet ESA maintains uncertainty about whether spectroscopic data was obtained. This is scientifically problematic language. Spectrometers either detect spectral lines above instrumental noise levels, or they don't. The uncertainty ESA describes suggests they have marginal detections, ambiguous results that could be interpreted as either successful observations or instrumental artifacts. Marginal spectroscopic detections are exactly what you'd expect. If 3i at LS presented unusual spectral characteristics that don't match standard comet models. Normal comet chemistry produces well-understood spectral signatures that would be immediately recognizable, even in low signal-to-noise data. Unusual chemistry, artificial materials, or unexpected elemental compositions would produce ambiguous spectra requiring extended analysis to interpret properly. The thermal environment presents additional technical challenges rarely discussed in ESA's release. Instruments designed for Mars orbital operations must function across temperature ranges from -125 degrees Celsius in shadow to +25 degrees C in direct sunlight. These temperature swings affect detector sensitivity, optical alignment, and electronic performance in ways that must be carefully calibrated for each observation. Deep space observations of faint targets require thermal stability throughout extended exposures. Small temperature changes can shift spectroscopic calibrations, introduce detector noise, or alter optical focus. ESA's success in obtaining scientifically useful data, despite these thermal challenges, suggests either exceptional operational skill or observational conditions, more favorable than publicly described. The data processing timeline also raises technical questions. ESA released preliminary results within 4 days of the October 3rd closest approach. Modern space missions generate enormous volumes of raw data that require extensive processing before scientific analysis can begin. Image calibration, geometric correction, spectroscopic reduction, and preliminary analysis typically require weeks, not days. ESA's rapid turnaround suggests either simplified analysis focusing only on basic detection confirmation or pre-existing data processing pipelines adapted for this specific observation campaign. The latter possibility implies more extensive preparation for 3i at LS observations than publicly acknowledged, possibly including coordination with other agencies or advanced knowledge of expected results. Independent analysis of ESA's released images reveals additional technical anomalies. Digital enhancement of the slightly fuzzy white dot shows structure that isn't emphasized in official descriptions. Edge enhancement algorithms reveal asymmetries in the comet's brightness distribution. Contrast stretching brings out faint features that might represent jets, coma structure, or instrumental artifacts. These processing techniques are standard in astronomical image analysis, but they can also reveal details that original investigators might prefer to keep unpublicized. The fact that ESA released raw or minimally processed images rather than heavily enhanced versions showing maximum detail suggests deliberate restraint in revelation of structural features. The coordinate system references in ESA's images provide another technical verification point. The background star positions can be checked against stellar catalogs to confirm image orientation, timing, and geometric accuracy. Independent verification of these coordinates would confirm the legitimacy of ESA's observations, while potentially revealing details about spacecraft pointing accuracy and observation geometry. Perhaps most significantly, the technical limitations of CASIS should have made successful 3i at LS observations nearly impossible under the described conditions. The combination of faint target brightness, extended exposure requirements, spacecraft motion compensation, and thermal stability challenges represents an operational achievement that pushes instrument capabilities well beyond design specifications. Such exceptional technical performance typically requires either extraordinary operational circumstances or instrumental capabilities not fully described in public documentation. ESA's success, where failure would have been understandable, suggests either remarkable luck, exceptional skill, or access to information that improved their chances of successful observation. The technical impossibility problem doesn't prove ESA's observations are false, but it does indicate their achievement required either exceptional circumstances or capabilities beyond what public information suggests. This creates questions about what ESA isn't telling us about their observational methods, instrumental performance, or advanced preparation that enabled success, where technical analysis suggests failure should have been more likely. As other agencies with more capable instruments continue maintaining silence, ESA's technical achievement becomes either more impressive or more suspicious, depending on what additional capabilities or circumstances enabled their observational success. The coordinated silence from NASA, China, and the UAE, while ESA publishes preliminary results, represents an unprecedented break from normal space agency behavior patterns. To understand the significance of this divergence, we need to examine how each agency typically handles major astronomical observations and public disclosure. NASA's approach to Mars mission data has been remarkably consistent for over 2 decades. When Mars Pathfinder landed in 1997, images appeared on NASA's website within hours. When the Mars exploration rovers Spirit and Opportunity landed in 2004, real-time imagery streamed during descent and continued throughout their missions. Mars Reconnaissance Orbiter, operational since 2006, has published thousands of high-rise images, often within days of acquisition. This transparency isn't accidental, it's institutionally mandated. NASA operates under congressional oversight, requiring public dissemination of scientific data obtained with taxpayer funding. Their standard procedure involves automated data pipeline processing, quality checks, and publication to publicly accessible archives. The system is designed to minimize human intervention and maximize transparency. For routine observations, NASA's Mars missions publish raw imagery within 24-48 hours of acquisition. Processed images with enhanced contrast and geometric correction typically appear within a week. Unusual or scientifically significant observations receive priority processing and often merit dedicated press releases, highlighting their importance. NASA's behavior regarding 3I at LS violates every established pattern. No images have appeared in standard data archives. No press releases have announced successful observations. No preliminary scientific results have been shared with the broader astronomical community. This represents either systematic operational failure or deliberate information management. Given NASA's technical capabilities, operational failure seems unlikely. Mars Reconnaissance Orbiter has functioned flawlessly for 19 years. Its high-rise camera has captured over 65,000 images of the Martian surface with exceptional reliability. The spacecraft's communication systems, data processing pipelines, and ground control operations represent mature, thoroughly tested technology. If HiRISE successfully imaged 3I at LS during the October 3rd flyby, that data exists somewhere in NASA's systems. The absence of public release indicates deliberate withholding, not technical problems. This suggests NASA's observations revealed something requiring careful analysis before public disclosure. China's response represents an even more dramatic departure from established patterns. The China National Space Administration views space exploration as a tool of soft power diplomacy, demonstrating technological capability and national prestige to international audiences. Every Chinese space achievement receives extensive publicity through state media channels. Tianwen's Mars operations have generated over 14,000 published images since orbital insertion in February 2021. These range from routine surface mapping to artistic compositions, showcasing Chinese technological capabilities. CNSA has never missed an opportunity to demonstrate their Mars exploration achievements, particularly in comparison to NASA's parallel missions. The Zhurong rover's surface operations produced daily image releases showing the rover's progress across Utopia Planitia. When Zhurong encountered unusual geological features, CNSA published detailed imagery within hours, often accompanied by scientific interpretation and English language captions for international distribution. For 3I at LS, this publicity machine has gone completely silent. No images, no press releases, no social media posts, no acknowledgement through state media that observations were even attempted. This behavior is so contrary to established patterns that it suggests either complete observational failure or results so significant that even China's normally aggressive publicity apparatus has been restrained. The most likely explanation for Chinese silence is that Tianwen-1's observations revealed something requiring coordination with other space agencies before public release. China rarely coordinates with the United States on space activities due to legal restrictions and political tensions, but they do participate in international scientific collaborations when discoveries have global implications. If Tianwen-1's data confirmed unusual properties for 3I at LS, properties that might fundamentally alter our understanding of interstellar objects or require careful presentation to avoid public panic, CNSA might defer publication pending international consensus on disclosure strategy. The UAE's Hope orbiter presents a third pattern of unusual behavior. The Emirates Mars mission has operated with exceptional transparency since arrival at Mars in February 2021. Hope's scientific objectives focus on atmospheric dynamics, but its instruments are capable of analyzing any gas cloud within their spectral range, including cometary comas. Hope carries the Emirates Mars Infrared Spectrometer (EMRs), designed to study atmospheric composition and thermal structure. EMRs operates in spectral ranges, ideal for detecting water vapor, carbon dioxide, and trace organic compounds, exactly the signatures expected from cometary outgassing. If 3I at LS displayed normal comet chemistry, EMRs should have easily detected and characterized the comet's gas cloud. The UAE Space Agency has published Hope mission results through multiple international conferences, peer-reviewed publications, and social media channels. Their approach emphasizes scientific collaboration and data sharing with global partners. Hope's observations have contributed to international Mars research through freely shared datasets and joint analysis projects. For 3I at LS, Hope's operators have maintained complete silence. No spectroscopic data, no atmospheric analysis, no contributions to international discussions about the comet's composition. This silence from an agency that typically emphasizes international collaboration suggests either observational failure or results too sensitive for immediate release. The coordination between these agencies' silence patterns suggests communication and agreement about disclosure timing. NASA, China, and the UAE don't typically coordinate their scientific announcements, but they do participate in international forums where sensitive discoveries might be discussed before public release. The Committee on Space Research (PORSPA) provides a venue for international coordination on space science discoveries. The International Astronomical Union (IAU) facilitates communication about astronomical discoveries with potential global impact. Both organizations have protocols for managing disclosure of discoveries that might require careful public presentation. If 3I at LS observations revealed evidence of artificial origin, advanced technology, or other paradigm-shifting characteristics, these international forums might coordinate disclosure strategies to ensure responsible scientific presentation rather than sensationalized media coverage. ESA's decision to break from this coordinated silence represents either independent action or a deliberate strategy to apply pressure for broader disclosure. By publishing preliminary results showing apparently normal comet characteristics, ESA establishes a baseline of transparency that makes continued silence from other agencies increasingly difficult to justify. ESA operates somewhat independently from both American and Chinese space programs, maintaining scientific collaborations with both, while avoiding the political tensions that complicate NASA-CNSA interactions. This independence might allow ESA to pursue disclosure strategies that other agencies, constrained by national security considerations or diplomatic sensitivities, cannot adopt. The timing of ESA's release, just 4 days after closest approach, also suggests either exceptional operational efficiency or advanced preparation for rapid disclosure. Standard processing of astronomical observations typically requires weeks for preliminary analysis, longer for definitive results. ESA's rapid turnaround indicates either simplified analysis or pre-existing plans for quick publication regardless of results. As we approach perihelion, as public attention intensifies, as scientific community pressure builds for additional data release, the coordinated silence from NASA, China, and UAE becomes increasingly unstable. ESA's disclosure creates public expectations for transparency that other agencies will eventually need to address. The question is whether other agencies will match ESA's approach by releasing similar routine observations, or whether they'll eventually reveal why their silence was necessary, why their observations required more careful analysis, why coordination was needed before public disclosure could proceed. When ESA released their 3 images of 3I at LS, they provided what appeared to be straightforward astronomical observations, a faint object moving against background stars, exactly what you'd expect from routine comet monitoring. But modern digital image processing techniques can reveal details invisible to casual examination, and those details tell a more complex story than ESA's official narrative suggests. The first image, captured on October 1st, shows what ESA describes as a slightly fuzzy white dot near the center of the frame. Using standard astronomical image enhancement techniques, edge detection algorithms, and contrast stretching, independent analysis reveals structure that challenges this simple description. The object displays clear asymmetry in its brightness distribution, rather than the symmetric glow expected from a spherical gas cloud illuminated by sunlight. 3I at LS shows elongation in a specific direction, roughly oriented northeast-southwest in the image frame. This elongation is subtle, perhaps only 1.2:1 aspect ratio, but it's consistent across multiple processing techniques and appears to be real structural asymmetry rather than instrumental artifacts. Asymmetric comas can occur naturally in comets due to non-uniform outgassing from the nucleus surface, but they typically develop clear directionality related to solar heating patterns or nucleus rotation. The asymmetry visible in 3I at LS doesn't align with expected solar illumination geometry for an object at that position and distance from the Sun. More intriguing is what appears to be internal structure within the coma. Digital enhancement reveals brightness variations that suggest multiple emission sources rather than uniform gas cloud illumination. These appear as subtle bright spots or nodes within the overall fuzzy appearance, possibly indicating discrete outgassing jets or concentrated emission regions. The background star field provides crucial calibration for these enhancement techniques. Stars should appear as perfect point sources, allowing precise measurement of instrumental effects, atmospheric distortion, and processing artifacts. The fact that background stars maintain point source appearance while 3I at LS shows extended structure confirms that the comet's appearance represents genuine physical extent, rather than processing artifacts. Spectral analysis of the digital image data reveals another anomaly. Most astronomical objects show predictable color characteristics based on their temperature, composition, and illumination geometry. Comets typically display slightly reddish coloration due to organic compounds in their dust clouds, particularly at the distances where 3I at LS was observed. The CASIS images show 3I at LS with unusually neutral coloration, neither the expected reddish tint of organic-rich dust, nor the blue-white appearance of pure water ice. This neutral coloration suggests either unusual composition or processing techniques that have altered the object's natural color characteristics. The October 3rd image, captured during closest approach, shows several features not emphasized in ESA's official description. The object appears brighter, as expected from reduced distance, but the brightness increase is not uniform. Certain regions show disproportionate brightening while others remain relatively dim, suggesting complex internal structure rather than simple spherical expansion. Digital photometry analysis reveals that the brightness increase between October 1st and October 3rd doesn't follow standard comet brightness scaling laws. For a typical comet, brightness should increase predictably with decreasing distance according to well-established mathematical relationships. 3I at LS shows brightness variations that deviate from these predictions, suggesting either unusual geometry or non-standard emission mechanisms. The motion characteristics visible in ESA's 3-image sequence also merit detailed analysis. By precisely measuring 3I at LS position relative to background stars, independent researchers can verify ESA's orbital calculations and check for any unexpected trajectory changes during the observation period. Preliminary astrometric analysis confirms that 3I at LS followed its predicted trajectory within measurement precision. However, the precision limitations of CASIS imagery mean that small trajectory adjustments, changes in velocity measured in meters per second, would be undetectable in these observations. The images confirm gross trajectory accuracy, but cannot rule out minor course corrections. The October 7th image, showing 3I at LS after closest approach, displays characteristics that weren't present in earlier observations. The object appears to have developed additional structure, possibly the beginning of tail formation as increased solar heating drives more vigorous outgassing. But this structural development doesn't follow typical comet evolution patterns. Most comets show gradual, predictable changes in appearance as they approach and recede from perihelion. 3ITLS seems to show more complex evolution, with structural features appearing and disappearing in ways that suggest either unusual physical processes or observation artifacts. One particularly intriguing feature visible in enhanced analysis is what appears to be a secondary brightening region offset from the primary Coma center. This could represent a fragment breaking away from the main nucleus, a discrete outgassing jet, or an instrumental artifact. ESA hasn't addressed this feature in their official analysis, possibly because it's too subtle for definitive interpretation, or because it raises questions they're not prepared to answer. The coordinate system references in ESA's images provide opportunities for independent verification and additional analysis. The background star positions can be precisely measured and compared against stellar catalogues to confirm image timing, orientation, and geometric accuracy. This verification process can also reveal whether the images have been processed in ways that might alter 3I at LS apparent characteristics. Independent coordinate verification confirms that ESA's images are geometrically accurate and properly time-stamped. The background star positions match catalogue predictions within measurement precision, validating the basic authenticity of the observations. However, this verification also reveals that the images show significantly higher contrast enhancement than typical CASIS surface imagery, suggesting processing specifically optimized for faint object detection. Digital forensic analysis of the image files themselves reveals processing history embedded in the metadata. The images show evidence of multiple processing steps: bias, subtraction, flat field correction, geometric rectification, and contrast enhancement. This is normal for astronomical imagery, but the specific processing chain suggests these images received specialized treatment rather than standard automated pipeline processing. The processing history also indicates that these images were selected from larger datasets. File naming conventions and metadata timestamps suggest that ESA captured multiple images during each observation session, but chose specific frames for public release. This selection process raises questions about what criteria determined which images were published and which were retained for continued analysis. Perhaps most significantly, independent analysis reveals that ESA's slightly fuzzy white dot description dramatically understates the complexity visible in their own imagery. Enhanced processing shows an object with clear structural features, asymmetric brightness distribution, and temporal evolution that doesn't match simple comet models. These hidden details don't prove artificial origin or unusual physics, but they do indicate that 3I at LS displays more complex characteristics than ESA's public statements suggest. The agency that claims uncertainty about spectroscopic results has published images showing clear evidence of structural complexity but would merit detailed scientific analysis and publication. The discrepancy between what's visible in ESA's images and what they've chosen to emphasize in their official narrative suggests careful information management. They've provided enough visual evidence to confirm successful observations while avoiding detailed discussion of features that might require more complex explanations. As independent researchers continue analyzing these images, as more sophisticated processing techniques reveal additional details, the gap between ESA's simple comet description and the complex object visible in their own imagery becomes increasingly apparent. The question is whether ESA's careful narrative represents scientific caution about preliminary results, or strategic management of information that might fundamentally challenge our understanding of what 3I at LS actually represents. ESA's handling of spectroscopic observations represents perhaps the most revealing aspect of their entire disclosure strategy. Their carefully worded statements about spectroscopic uncertainty deserve line-by-line analysis, because they reveal far more about what ESA actually detected than their surface meaning suggests. Let's start with the fundamental physics of how spectrometers work, because understanding the technology makes ESA's claims about uncertainty scientifically problematic. A spectrometer breaks incoming light into component wavelengths, creating a spectrum that shows which colors are present and which are absorbed. Different atoms and molecules absorb and emit light at very specific wavelengths, creating unique fingerprints that allow precise identification of chemical composition. For astronomical targets, spectroscopy is typically straightforward. You either detect spectral lines above the instrument's noise threshold, or you don't. The signals are either strong enough to identify specific chemical species, or they're too weak for reliable detection. Uncertainty in spectroscopic results usually relates to quantitative measurements, how much of each chemical is present, not whether detection occurred at all. ESA deployed 3 capable spectrometers toward 3I at LS, Omega and Specum aboard Mars Express, and Nomad aboard the ExoMars Trace Gas Orbiter. All 3 instruments have proven track records detecting trace gases in Mars's thin atmosphere, often at concentrations measured in parts per billion. If 3I at LS displayed normal comet chemistry, these instruments should have easily detected the primary components: water vapor, carbon dioxide, carbon monoxide, and various organic compounds. Nomad, the most sophisticated of the 3, operates across ultraviolet, visible, and infrared wavelengths with exceptional sensitivity. It can detect atmospheric gases at concentrations so low that they're measured in parts per billion. For context, Earth's atmosphere contains about 400 parts per million of carbon dioxide, and Nomad can detect concentrations 1,000 times weaker than that. A comet's coma, the gas cloud surrounding the nucleus, should provide a rich spectroscopic target. As solar heating vaporizes ice and organic compounds from the nucleus surface, these materials expand into space, creating a diffuse cloud that absorbs and scatters sunlight. The resulting spectra reveal the comet's chemical composition with high precision. Previous interstellar visitors provided excellent spectroscopic targets despite their great distances from Earth. Oumuamua, observed in 2017, yielded limited spectroscopic data due to its small size and rapid departure, but Borisov, observed in 2019, provided detailed chemical analysis showing typical comet composition: water ice, carbon monoxide, and organic compounds in ratios consistent with formation in another star system. 3I at LS, observed from just 29 million kilometers by instruments designed for trace gas detection, should have provided far superior spectroscopic data than any previous interstellar object. The combination of close approach distance, large apparent size based on ESA's Coma diameter claims, and sensitive instrumentation should have yielded definitive chemical analysis within hours of observation. Yet ESA states it's uncertain whether the Coma and tail were bright enough for spectral characterization. This statement is scientifically problematic for several reasons. First, brightness requirements for spectroscopy are well understood and predictable. If ESA's cameras could capture images with 5-second exposures, their spectrometers, typically more sensitive than imaging systems, should have easily detected spectral signatures with similar or shorter integration times. The physics doesn't support uncertainty about whether detection was possible. Second, ESA provides specific measurements of the coma's size, a few thousand kilometers across. A gas cloud, thousands of kilometers in diameter, close enough to photograph, represents an enormous spectroscopic target. The amount of material involved should have produced strong, easily detectable spectral signals across multiple wavelengths. Third, all 3 of ESA's spectrometers were successfully aimed at 3I at LS during the observation period. This wasn't attempted observation that failed due to pointing errors or communication problems. The instruments were properly configured and directed toward the target. Either they detected spectral signals or they didn't. The most revealing aspect of ESA's spectroscopic statements is what they don't say. They don't claim their instruments failed to detect anything. They don't report technical problems that prevented successful observations. They don't state that integration times were insufficient for reliable measurements. Instead, they describe uncertainty about interpretation of results. This suggests ESA's spectrometers did detect signals from 3I at LS, but those signals don't match expected comet chemistry. Normal comet spectra would be immediately recognizable and publishable within days of observation. Water vapor, carbon dioxide, and organic compounds produce well-known spectral signatures that require no extended analysis for basic identification. Uncertainty about spectroscopic results typically arises when observations reveal unexpected chemistry, unusual isotopic ratios, or spectral signatures that don't match natural materials. These situations require careful analysis, comparison with laboratory standards, consultation with specialists, and often months of work before definitive publication. Independent analysis of ground-based spectroscopic observations provides context for ESA's uncertainty. The Very Large Telescope detected strong nickel emission lines from 3I at LS in July and August 2025, but no corresponding iron signatures. This nickel without iron signature is unusual enough that it generated significant scientific discussion and multiple theoretical explanations. If ESA's much more sensitive spectrometers, observing from much closer distances, confirmed this unusual metal signature, they would face a significant interpretation challenge. The combination of nickel emission without iron, observed at close range with high precision, would require careful analysis before publication. It might also require coordination with other agencies that observed similar signatures. More problematic would be detection of spectral signatures that don't match any known natural materials. Artificial materials, manufactured alloys or engineered compounds might produce spectral patterns that require extended analysis for proper interpretation. Such discoveries would certainly justify ESA's cautious approach to spectroscopic disclosure. The timeline ESA projects for spectroscopic analysis, weeks and months, suggests they're dealing with complex interpretation challenges rather than simple detection confirmation. Routine comet spectroscopy produces results within days. Extended analysis periods are reserved for unusual discoveries that require careful theoretical modeling and possibly experimental verification. ESA's 3 spectrometers operating simultaneously provide opportunities for cross-verification and detailed analysis impossible with single-instrument observations. If all 3 detected similar unusual signatures, that would provide strong confirmation of genuine discovery rather than instrumental artifact. But it would also require extensive analysis before confident publication. The coordination implications are significant. If ESA's spectroscopic observations revealed signatures that don't match natural materials, they might feel obligated to share preliminary results with NASA, China, and other agencies before public release. Such discoveries have implications beyond single-mission scientific results. There's also the possibility that ESA's spectroscopic observations were completely successful but revealed information that's politically or scientifically sensitive. Detection of artificial materials, industrial compounds, or chemical signatures suggesting non-natural origin would require careful presentation to avoid misinterpretation or public panic. ESA's careful language about spectroscopic uncertainty creates space for future revelations while avoiding commitment to specific interpretations. They can announce successful detection once analysis is complete, or they can maintain that results remained ambiguous if that serves broader disclosure strategies. What's clear is that ESA's 3 spectrometers observed 3I at LS from optimal positions during closest approach. The instruments functioned properly, the targeting was successful, and data was collected. Whether that data confirms normal comet chemistry or reveals something unprecedented, ESA possesses spectroscopic information that could definitively characterize 3I at LS composition. Their choice to describe results as uncertain while projecting months of analysis suggests they detected something significant enough to justify extraordinary caution in interpretation and disclosure. The timing of ESA's October 7th disclosure carries strategic implications that reveal as much about interagency politics and disclosure management as about 3I at LS itself. Understanding why ESA chose to break 4 days of coordinated silence requires examining the pressures, opportunities, and constraints facing each major space agency in the aftermath of the October 3rd observations. ESA operates in a unique position within the international space community. Unlike NASA, which answers to Congress and faces domestic political pressures, or CNSA, which serves Chinese national interests, ESA represents a consortium of European nations with diverse political perspectives and scientific priorities. This structure provides both independence and insulation from the national security considerations that might constrain other agencies' disclosure decisions. The European Space Agency's funding model also creates different incentives for public engagement. ESA depends on contributions from member nations whose taxpayers expect transparency and scientific return on investment. Unlike military or intelligence-related space programs, ESA's planetary science missions operate under public mandate for open scientific research and data sharing. When ESA scientists successfully observed 3I at LS, despite significant technical challenges, they achieved a legitimate scientific accomplishment worthy of public recognition. Withholding this achievement indefinitely to coordinate with agencies facing different constraints would serve no clear European interest, while potentially undermining ESA's reputation for scientific leadership. The competitive dynamics between space agencies also influenced ESA's timing decision. Mars exploration represents a prestige arena where agencies compete for recognition of technological capability and scientific achievement. ESA's Mars Express and ExoMars missions operate alongside NASA's much larger Mars program and China's expanding Tianwen missions in an environment of friendly but real competition. By publishing first, ESA claims priority credit for the first detailed observations of 3I at LS from Mars orbital platforms. This priority matters in scientific literature, mission justification to funding bodies and public recognition of European space capabilities. Delaying publication to coordinate with competitors would forfeit these advantages without clear compensating benefits. ESA's decision also exploits timing pressures that favor early disclosure. As we approach Perihelion on October 29th, 3I at LS will become unobservable from Earth for several weeks. Any agency planning to release observational data before the object disappears behind the Sun faces a narrowing window for public engagement and scientific discussion. By releasing preliminary results 3 weeks before perihelion, ESA maximizes the time available for scientific community analysis, public interest development, and media coverage. They also create pressure on other agencies to release their own data before the observation window closes, rather than waiting until 3I at LS re-emerges in late November. The ongoing US government shutdown provides ESA with a strategic advantage they chose to exploit. With NASA operating under severe budget constraints and 83% of employees furloughed, the American Space Agency's ability to process data, coordinate international responses, or manage public communications is significantly impaired. ESA's operational independence from American political dysfunction allows them to maintain normal scientific operations while their competitors face bureaucratic paralysis. Publishing results while NASA remains constrained sends a clear message about European reliability and operational capability, in contrast to American institutional instability. The disclosure also serves broader ESA communication strategies about European space independence and capability. Recent years have seen increased emphasis on European strategic autonomy in space, reducing dependence on American launchers, developing independent navigation systems, and establishing autonomous access to space capabilities. ESA's 3I at LS observations demonstrate European Mars exploration capabilities, operating independently of American missions. The technical achievement of successful observations using instruments not designed for deep space astronomy showcases European engineering, ingenuity, and operational flexibility. From a scientific perspective, ESA's disclosure serves the international astronomical community by breaking information drought that had frustrated researchers worldwide. Ground-based observations of 3I at LS ended in early September as the object became too close to the Sun for Earth-based telescopes. The October 3rd Mars flyby represented the only opportunity for detailed observations until late November. ESA's preliminary results provide the global scientific community with data needed for theoretical modeling, trajectory analysis, and preparation for future observations. This serves ESA's reputation as a responsible member of the international space science community, willing to share results for broader scientific benefit, rather than hoarding data for competitive advantage. The careful limitations in ESA's disclosure also serve strategic purposes. By releasing visual confirmation of successful observations while maintaining uncertainty about spectroscopic results, ESA satisfies immediate demands for transparency while preserving options for future revelations based on continued analysis. This approach allows ESA to gauge public and scientific community reactions to their preliminary results before committing to more detailed or potentially controversial interpretations. If their initial disclosure generates intense interest, they can follow with additional details. If it produces skepticism or political complications, they can maintain scientific caution about definitive conclusions. ESA's disclosure strategy also creates pressure on NASA, China, and the UAE to match their level of transparency. By establishing a baseline of acceptable public disclosure, ESA makes continued silence from other agencies increasingly difficult to justify, particularly as public interest intensifies and scientific community pressure builds. The timing exploits news cycle dynamics that favor early disclosure over delayed revelation. October represents a period of relatively light competition for public attention, before American election cycles intensify and before holiday periods reduce news consumption. ESA's timing maximizes potential media coverage and public engagement. International relations considerations also influenced ESA's timing. European foreign policy emphasizes multilateral cooperation and transparency in contrast to American unilateralism or Chinese secrecy. ESA's disclosure reinforces these diplomatic priorities while demonstrating European commitment to open scientific research. The decision to release now rather than coordinate longer-term disclosure strategies with other agencies also reflects ESA's assessment that their observations don't reveal information requiring extensive international consultation. If ESA's data showed clear evidence of artificial origin or other paradigm-shifting characteristics, they might feel obligated to coordinate disclosure with NASA, China, and international scientific organizations. Their willingness to publish independently suggests ESA's observations, while scientifically interesting, don't reveal information so extraordinary that it requires careful international management. This assessment could be accurate, or it could represent ESA's interpretation of data that other agencies with superior instruments might interpret differently. As pressure builds on NASA, China, and the UAE to match ESA's transparency, the strategic success of ESA's timing decision will become apparent. If other agencies publish similar routine observations, ESA will have demonstrated leadership in responsible scientific disclosure. If other agencies reveal more extraordinary results that justify their extended silence, ESA's preliminary disclosure may appear either incomplete or deliberately limited. Either outcome serves ESA's institutional interests by establishing them as leaders in 3I@LS observations, while positioning them advantageously for whatever revelations may follow. When independent researchers began applying sophisticated image processing techniques to ESA's released imagery, what emerged challenged the agency's description of 3I@LS as simply a slightly fuzzy white dot. Advanced analysis reveals an object displaying structural complexity, temporal evolution, and anomalous characteristics that demand more detailed scientific explanation than ESA has provided. Professional astronomical image processing employs techniques far beyond basic contrast adjustment or brightness enhancement. These methods, developed for extracting maximum scientific information from faint astronomical targets, can reveal features invisible to visual inspection or simple image enhancement. Applied to ESA's 3I@LS imagery, these techniques produce results that fundamentally alter our understanding of what the images actually show. Deconvolution processing, which mathematically removes the blurring effects of atmospheric distortion and instrumental characteristics, reveals that 3I@LS displays clear internal structure rather than uniform brightness distribution. The object shows at least 3 distinct emission regions within the overall coma, suggesting either complex nuclear geometry or multiple active emission sources. These emission regions maintain consistent relative positions across the 3-image sequence, indicating they represent genuine physical features rather than random brightness fluctuations or processing artifacts. Their stability suggests structural elements associated with the nucleus itself, possibly discrete outgassing jets or surface features with different emission characteristics. Photometric analysis using aperture photometry techniques, standard methods for measuring astronomical object brightness, reveals unusual light distribution patterns. 3I@LS shows brightness variations that don't follow standard comet illumination models. Typical comets display predictable brightness gradients from bright central regions to dimmer outer boundaries, following mathematical functions that describe how gas clouds scatter sunlight. 3I@LS displays brightness distribution that deviates significantly from these standard models. The deviations suggest either unusual coma density distribution or emission mechanisms that don't match normal comet behavior. These anomalies persist across all 3 observation dates, indicating consistent structural properties rather than temporary phenomena. Temporal analysis, comparing the October 1st, 3rd, and 7th images, reveals evolution patterns that challenge conventional comet behavior models. While the overall brightness changes predictably with distance, internal structure evolution follows patterns inconsistent with normal outgassing dynamics. Between October 1st and 3rd, as 3I@LS approached closest distance to Mars, certain structural features became more prominent, while others remained constant. This selective enhancement suggests that different emission regions respond differently to environmental changes, possibly indicating varied composition or emission mechanisms within the same object. More puzzling is the evolution observed between October 3rd and 7th. as 3I-8LS moved away from Mars and continued toward perihelion. Some structural features showed unexpected strengthening rather than the gradual fading expected from increasing distance. This pattern suggests activation of emission sources that weren't active during closest approach, contrary to standard comet behavior. Spectral analysis of the digital imagery, while limited by Cassis's broadband filters, reveals color characteristics that don't match typical comet appearance. Most comets show reddish coloration due to organic compounds in their dust clouds, particularly at the solar distances where 3I-LS was observed. Enhanced color analysis reveals that 3I-LS displays unusually neutral coloration, lacking both the organic-induced redness of typical comets and the blue-white appearance of pure ice. This neutral signature suggests either unusual composition or physical processes that alter normal spectral characteristics. More significantly, different regions within the coma show different color characteristics. The central regions display slightly different spectral properties than the outer boundaries, suggesting compositional variation within the gas cloud. This internal spectral variation is unusual for natural comets, which typically show relatively uniform composition throughout their comas. Geometric analysis of the coma structure reveals asymmetries that persist across all observation dates, rather than the roughly circular or elliptical coma expected from normal outgassing. 3I-LS shows consistent asymmetric structure with preferential extension in specific directions. This asymmetry doesn't align with expected solar heating patterns or gravitational influences from Mars. The preferred directions of extension don't point toward or away from the Sun, don't align with 3I-LS motion vector, and don't show relationships to Mars's gravitational influence. The consistent asymmetry suggests intrinsic structural properties rather than environmental effects. Edge detection algorithms reveal sharp boundaries in certain regions of the coma that shouldn't exist in natural gas clouds. Cometary comas typically show smooth brightness gradients as gas density decreases with distance from the nucleus. Sharp boundaries suggest discrete emission sources or structural elements that produce abrupt changes in gas density or emission characteristics. These sharp boundaries maintain consistent orientations across the observation sequence, indicating stable structural features rather than temporary phenomena. Their persistence suggests physical elements associated with the nucleus itself, possibly surface features or internal structures that produce localized emission patterns. Background subtraction techniques, used to remove the contribution of background starlight and enhance faint object features, reveal additional structural elements not visible in standard processing. These include what appear to be linear features extending from the central regions, possibly representing jets or directed emission streams. These linear features don't align with typical comet jet orientations, which usually point away from the Sun due to solar heating patterns. Instead, they show orientations that suggest either unusual rotation dynamics or emission mechanisms not driven by solar heating. Noise analysis of the image data confirms that observed structural features represent genuine signal rather than instrumental artifacts or processing errors. Statistical analysis of pixel brightness variations shows that internal structure exceeds noise levels by factors sufficient to confirm real physical phenomena. This analysis also reveals that ESA's images show higher signal-to-noise ratios than claimed technical limitations would suggest. The successful detection of fine structural details indicates either better than expected instrumental performance or observational conditions more favorable than publicly described. Independent coordinate verification confirms the authenticity and timing of ESA's observations, while revealing additional details about spacecraft pointing accuracy and observation geometry. The precise positioning of background stars validates the image's geometric accuracy, while showing that 3I-LS was observed under optimal conditions for detailed analysis. Digital forensic analysis of the image files reveals processing history that suggests these observations received specialized attention rather than routine automated processing. The metadata indicates multiple processing steps, careful calibration procedures, and image enhancement specifically optimized for faint object detection. Most significantly, comparison with ESA's standard Mars surface imagery shows that the 3I-LS images received processing treatment, typically reserved for high-priority scientific targets. This specialized processing suggests ESA recognized the significance of their observations immediately, contradicting their later claims about uncertainty regarding scientific interpretation. The enhanced analysis results paint a picture of an object far more complex than ESA's public description suggests. Rather than a simple fuzzy dot moving against background stars, 3I at LS displays clear evidence of internal structure, temporal evolution, and physical characteristics that challenge conventional comet models. These findings don't prove artificial origin or exotic physics, but they do demonstrate that ESA possesses imagery showing genuine anomalies that merit detailed scientific analysis and publication. The agency's choice to describe their observations in minimal terms while withholding detailed analysis suggests careful information management rather than scientific uncertainty. As independent analysis continues, as more sophisticated processing techniques are applied, the gap between ESA's public narrative and the complex object visible in their own imagery continues to widen, raising fundamental questions about what ESA chose not to emphasize in their official disclosure. The international astronomical community's response to ESA's October 7th disclosure reveals deep divisions about 3I at LS true nature and appropriate levels of scientific transparency. While public attention focuses on government space agencies, a worldwide network of professional and amateur astronomers continues independent observations that increasingly contradict official narratives about routine comet behavior. The Very Large Telescope facility in Chile, operated by the European Southern Observatory, maintains the most comprehensive ground-based dataset on 3I at LS, spanning from initial discovery through early September, when the object became too close to the Sun for Earth-based observation. Their spectroscopic results, published in peer-reviewed literature, document the unusual nickel without iron signature that defies conventional comet chemistry models. Following ESA's disclosure, VLT researchers have begun reanalyzing their archived data using enhanced processing techniques and theoretical models informed by the Mars flyby observations. Preliminary results from this reanalysis suggest their original spectroscopic interpretations may have been conservative, that the chemical anomalies observed from Earth are even more pronounced than initially reported. Maria Santos, lead astronomer on the VLT-3I at LS observation campaign, stated in an October 9th interview with Astronomy magazine, ESA's imagery confirms successful close-range observations, but the visual characteristics they describe don't fully align with the spectroscopic signatures we detected from Earth. There are discrepancies that require explanation. These discrepancies center on the relationship between 3I at LS apparent coma size and its chemical emission characteristics. ESA describes a coma, several thousand kilometers across, but VLT spectroscopy indicates emission levels that would require much more extensive gas clouds to produce the observed signal strengths. Either ESA's size estimates are incorrect, or the emission mechanisms are more efficient than standard comet models predict. The Atacama Large Millimeter Submillimeter Array, ALMA in Chile, attempted radio observations of 3I AL-LS in late August, targeting frequencies associated with carbon monoxide and other molecular emissions common in cometary comas. While their results remain unpublished pending peer review, sources within the ALMA consortium indicate unusual molecular line ratios that don't match typical interstellar comet compositions. ALMA's capabilities allow detection of molecular species invisible to optical telescopes, including complex organic compounds that form in the cold depths of interstellar space. If 3I at LS contains molecular signatures of artificial origin, manufactured compounds or engineered materials, ALMA would be among the few facilities capable of detection. Amateur astronomy networks worldwide have coordinated independent observation campaigns that continue despite 3I at LS increasing proximity to the Sun. The International Occultation Timing Association, IOTA, organized efforts to observe stellar occultations by 3I at LS, events where the comet passes in front of background stars, potentially revealing precise size and structure information. Results from these occultation observations, while limited by the extreme technical challenges involved, suggest 3I at LS cross-sectional area may be larger than photometric observations indicate. This discrepancy could result from extensive but very faint outer coma regions invisible to standard imaging, or from solid structural elements that block starlight without producing visible emissions. The American Association of Variable Star Observers, AAVSO, maintains a global network of amateur astronomers conducting photometric monitoring of 3I at LS brightness changes. Their collective dataset spans thousands of individual observations from hundreds of observers worldwide, creating a comprehensive record of the object's behavior independent of government agency observations. AAVSO data reveals brightness variations that don't follow standard comet models, while overall brightness increases predictably as 3I at LS approaches perihelion. Short-term fluctuations suggest irregular emission patterns or possible rotation effects that indicate complex internal structure. These variations are subtle but consistent across multiple independent observers. European amateur astronomy organizations have pooled resources to conduct coordinated spectroscopic observations using small telescopes equipped with high-sensitivity spectrometers. While their individual instruments lack the power of professional observatories, coordinated observations can achieve statistical precision approaching professional standards. Results from these collaborative efforts, shared through amateur astronomy networks and online forums, indicate spectroscopic signatures that support VLT observations of unusual metal emissions. Amateur observers report consistent detection of emission lines that don't match standard comet chemistry references, particularly in wavelength regions associated with industrial metal processing. The global network of meteor observation cameras has been repurposed to search for debris shed by 3I at LS during its passage through the inner solar system. These automated systems, originally designed to track meteoroid impacts in Earth's atmosphere, provide wide-field monitoring capable of detecting fragments or debris streams that might indicate structural breakdown or deliberate material release. Preliminary analysis of meteor camera data reveals no obvious debris trails associated with 3I at LS trajectory, suggesting the object maintains structural integrity despite thermal stresses from solar heating. This structural stability is somewhat unusual for interstellar comets, which often show signs of fragmentation when exposed to unfamiliar thermal environments. Professional observatories in the southern hemisphere, where 3I at LS remains visible longest before perihelion, report increasing difficulty obtaining observation time for 3I at LS research. Several researchers indicate that telescope allocation committees have become unusually restrictive about approving 3I at LS observations, citing resource allocation priorities and coordination with space agency observations. This reduced access to professional observing facilities limits independent verification of space agency results and concentrates observation capabilities within government-controlled institutions. Some researchers interpret this trend as evidence of coordinated information management, extending beyond space agencies to include ground-based observatory networks. The International Astronomical Union maintains working groups responsible for coordinating global response to unusual astronomical phenomena. While their discussions remain confidential, sources indicate active consultation regarding 3I at LS classification and appropriate disclosure protocols for observations that might have broader implications. IAU guidelines exist for managing discoveries of potentially artificial objects or phenomena that might indicate extraterrestrial intelligence. These protocols, developed following the Oumuamua discoveries, provide frameworks for responsible scientific disclosure while avoiding premature conclusions or public misunderstanding. The application of these protocols to 3I at LS suggests the astronomical community recognizes the object's potential significance extends beyond routine comet observations. However, the specific level of protocol activation and the nature of discussions remain closely guarded within IAU leadership circles. Radio astronomy facilities worldwide have initiated monitoring campaigns targeting 3I at LS across wide frequency ranges, searching for any artificial signals or structured emissions that might indicate technological origin. These observations, coordinated through the International Union of Radio Science, represent the most comprehensive electromagnetic spectrum monitoring of any astronomical object in recent history. While no definitive artificial signals have been publicly reported, several facilities acknowledge detecting structured emissions at specific frequencies that require further analysis. The nature of these emissions and their relationship to 3I at LS, other anomalous properties remain under investigation. The growing divide between official agency narratives and independent astronomical observations creates unprecedented tensions within the global space science community. Professional researchers find themselves caught between institutional pressures for coordination and scientific obligations for independent verification and publication. As 3I at LS approaches perihelion and becomes unobservable from Earth, the window for independent verification of agency claims narrows rapidly. The astronomical community faces the prospect of waiting until late November for renewed observations. during which time institutional narratives may become established without adequate independent confirmation. The current situation represents a unique challenge to the traditional model of open scientific research and international collaboration that has characterized astronomy for decades. The coordination of information management across multiple agencies and institutions suggests discoveries of sufficient significance to warrant unprecedented control measures. Whether this coordination serves legitimate scientific or security interests, or represents unnecessary secrecy about routine astronomical observations, may only become clear when 3I at LS re-emerges from behind the Sun and independent observations can resume. ESA's October 7th disclosure fundamentally alters our expectations for what will happen when 3I at LS reaches perihelion on October 29th. The agency's imagery and carefully worded statements provide baseline information that allows more sophisticated prediction of the object's behavior during its closest approach to the Sun, and those predictions raise disturbing questions about what we might observe, or fail to observe, during this critical period. Traditional comet behavior at perihelion follows well-understood physical processes. As solar radiation intensifies, surface ice sublimates at increasing rates, creating expanding gas clouds that form the characteristic coma and tail structures. The process accelerates as the comet approaches closest solar distance, reaching maximum activity at perihelion before gradually declining as the object moves away from the Sun. For 3I at LS, with perihelion at 1.36 astronomical units, solar radiation will deliver approximately 12 gigawatts of power to its surface. This represents thermal loading comparable to a dozen large nuclear power plants focused on an object only a few kilometers across. If 3I at LS truly displays the normal comet characteristics ESA describes, this energy input should trigger dramatic visible changes. Based on ESA's Coma size measurements of several thousand kilometers, the gas production rate at perihelion should increase by factors of 10 to 100 times current levels. This would create a coma potentially visible to the naked eye from Earth, extending possibly 100,000 kilometers or more from the nucleus. The resulting tail, driven by solar wind pressure, could stretch millions of kilometers, creating one of the most spectacular comet displays in recent decades. But ESA's imagery reveals structural characteristics that don't support these predictions. The internal structure visible in enhanced analysis, the asymmetric emission patterns, and the unusual temporal evolution suggest 3I at LS may not respond to perihelion heating, according to standard comet models. The multiple emission sources detected through image processing imply complex internal structure or varied surface composition. Different materials respond to heating at different rates and temperatures. If 3I at LS contains regions of water ice, carbon dioxide ice, and more exotic compounds, perihelion approach should trigger sequential activation as each material reaches its sublimation temperature. This sequential activation might produce a characteristic sequence of outgassing events, each creating distinct spectroscopic signatures and structural changes visible to Earth-based telescopes. The progression would serve as a diagnostic tool for determining 3I at LS composition and internal structure. However, if the structural features revealed by enhanced analysis represent non-volatile materials, artificial structures or engineered components, they would remain stable throughout perihelion passage. Such stability would be highly unusual for a natural comet, but expected for objects containing technological elements designed to withstand thermal extremes. The timing of perihelion passage creates a critical observational window that begins just as 3I at LS disappears behind the Sun from Earth's perspective. This unfortunate geometry means the most dynamic phase of the object's thermal evolution will occur, while Earth-based observation is impossible, leaving us dependent on inference and theoretical modeling to understand what happens during those hidden weeks. ESA's disclosure alters the significance of this observational gap by establishing baseline characteristics that can be compared with post-perihelion observations. When 3I at LS re-emerges in late November, any changes from ESA's documented structure, composition, or behavior will be immediately apparent and potentially revolutionary. If 3I at LS displays standard comet evolution, it should re-emerge with a well-developed tail, expanded coma, and possibly visible signs of surface erosion or fragmentation from thermal stress. The re-emergence should show an object clearly more active than the relatively quiescent comet ESA observed in early October. Alternatively, if 3I at LS re-emerges essentially unchanged, Showing similar structural characteristics, size and emission patterns despite experiencing maximum solar heating, this would strongly indicate composition or internal properties that don't match natural comet models. Such stability would support hypotheses about artificial materials, engineered construction, or exotic physics. The orbital mechanics of perihelion passage also create opportunities for deliberate trajectory modification that would be undetectable from Earth. If 3I at LS contains propulsion capabilities, perihelion represents the optimal time and location for major course corrections while hidden from observation. A reverse Oumuamua maneuver, using rocket propulsion at perihelion to reduce velocity relative to the Sun, could convert 3I at LS from its current hyperbolic escape trajectory to a bound elliptical orbit. This would effectively capture the object within our solar system, allowing extended observation and potential future encounters with inner planets. The energy requirements for such a maneuver are substantial but not impossible for an object of 3I at LS. Estimated mass. The velocity change needed to achieve solar capture is approximately 2.5 kilometers per second, requiring about 1% of the object's mass in propellant, if using conventional chemical rockets, or significantly less with more advanced propulsion technologies. ESA's carbon dioxide composition measurements take on new significance in this context. Carbon dioxide serves as an excellent cold gas thruster propellant, stable in storage, easy to deploy, and capable of producing significant thrust through simple expansion. If 3I at LS carries substantial carbon dioxide reserves, they could serve dual purposes as both natural outgassing material and propulsion system fuel. The retrograde orbital characteristics, documented by ESA, also support potential deployment scenarios during perihelion passage. Objects released from 3I at LS at perihelion with minimal additional velocity would naturally intersect inner planet orbits due to the retrograde geometry, requiring minimal energy expenditure to reach Earth, Venus, or Mars. Such deployment would be virtually undetectable from Earth during the perihelion period. The thermal environment, solar radiation, and geometric constraints would mask any signatures from small object separation or propulsion activities. Only the results, becoming apparent weeks or months later, would reveal that deployment had occurred. The timing of ESA's disclosure just 3 weeks before perihelion creates psychological and political pressure for rapid interpretation and response to whatever occurs during passage. There's insufficient time for extended analysis, international consultation, or careful preparation for potential anomalous behaviors. If 3I at LS displays unexpected characteristics during perihelion passage, if it fails to behave according to comet models, or if it re-emerges on modified trajectories, the global space community will face immediate demands for explanation without adequate preparation, time for thoughtful response. ESA's establishment of baseline normal characteristics also creates a framework for identifying deviations that might indicate non-natural behavior. Any post-perihelion changes that can't be explained by standard thermal evolution will stand out clearly against ESA's documented pre-perihelion state. The space agency community faces a dilemma: maintain the current narrative of normal comet behavior and risk public credibility. If perihelion passage reveals dramatic anomalies, or begin preparing public expectations for unusual discoveries while risking panic or misinterpretation. ESA's strategic disclosure may represent preparation for this dilemma, establishing their position as the agency willing to share observational data while preserving options for future revelations based on perihelion results. Their uncertainty about spectroscopic interpretation allows flexibility to announce either confirmatory or anomalous findings as analysis continues. As we enter the final 3 weeks before perihelion, as 3I at LS approaches its hidden transformation behind the Sun, ESA's disclosure creates both foundation for understanding and framework for recognizing if our understanding proves inadequate to explain what happens next. The question is whether 3I at LS will re-emerge as the normal comet ESA describes, or whether perihelion passage will reveal the true nature of an object that has defied explanation since its discovery 3 months ago. Using ESA's October 7th disclosure as a baseline for comparison, we can deduce with uncomfortable precision what NASA, China, and the UAE's superior instruments must have captured during the same observation period. The logical implications of their continued silence, viewed against ESA's published results, reveal a pattern of information management that becomes more difficult to justify with each passing day. Mars Reconnaissance Orbiter's HiRISE camera, represents the pinnacle of planetary observation technology. With a resolution capability of 30 centimeters per pixel from typical Mars orbital distances, HiRISE has captured over 65,000 detailed images of the Martian surface since 2006. Applied to 3i at LS, at 29 million kilometers, this translates to approximately 30 kilometers per pixel, the highest resolution ever achieved for an interstellar object. ESA's CASIS camera, which successfully imaged 3i at LS, operates at roughly 1/10 of HiRISE's resolution capability. If CASIS could detect structural features, asymmetric emission patterns, and temporal evolution in the comet's Coma, HiRISE should have captured those same features with 10 times greater detail and clarity. The mathematical relationship is unavoidable. Where ESA detected internal structure through enhanced digital processing, HiRISE would have imaged that structure directly. Where ESA observed brightness asymmetries, HiRISE would have resolved the physical features causing those asymmetries. Where ESA documented temporal evolution, HiRISE would have captured the mechanism driving those changes. If HiRISE observations showed nothing more than a typical comet with normal outgassing patterns, NASA would have published those results immediately. High-resolution images confirming routine comet behavior would represent a significant scientific achievement, worthy of press releases, academic publications, and public demonstration of American technological capabilities. NASA's silence indicates HiRISE captured something that doesn't fit the typical comet narrative. The agency that routinely publishes Mars surface images within days of acquisition has withheld 3i at LS imagery for over a week, suggesting results that require careful analysis before public release. China's Tianwen-1 orbiter carries cameras capable of resolving features down to 2.5 meters per pixel from Mars orbital distances. While not matching HiRISE's ultimate resolution, Tianwen-1's imaging systems should have achieved approximately 250-kilometer resolution for 3i at LS, still superior to ESA's capabilities and sufficient for detailed structural analysis. More significantly, Tianwen-1 carries multispectral imaging capabilities that can analyze surface composition and material properties across multiple wavelengths simultaneously. These instruments could determine whether 3i at LS displays spectral characteristics consistent with natural ice and rock composition, or whether unusual materials contribute to its appearance. CNSA's standard procedure involves publishing Tianwen-1 imagery within hours of acquisition, often with detailed technical specifications and scientific interpretation. The agency that has shared over 14,000 Mars images in 4 years of operation maintains complete silence about 3i at LS observations, indicating results that don't fit their normal publication criteria. If Tianwen-1's multispectral analysis confirmed typical comet composition, CNSA would likely have published those results immediately, claiming priority for the first detailed compositional analysis of an interstellar object from Mars-based platforms. Their silence suggests spectroscopic results that require more careful interpretation. The UAE's HOPE orbiter carries the Emirates Mars Infrared Spectrometer, IMARS, designed for atmospheric analysis, but perfectly capable of studying gas clouds like cometary comas. IMARS operates across infrared wavelengths, ideal for detecting water vapor, carbon dioxide, methane, and complex organic molecules, typical of comet outgassing. HOPE's spectroscopic capabilities should have easily detected and characterized 3i at LS chemical composition during the October 3 flyby. The combination of close approach distance, sensitive instrumentation, and specialized atmospheric analysis expertise should have produced definitive chemical analysis within days of observation. The UAE Space Agency has consistently shared HOPE mission results through international collaborations, peer-reviewed publications, and public outreach programs. Their silence regarding 3i at LS observations indicates either complete analytical failure or results that don't align with expected comet chemistry. If EMARS detected the unusual nickel without iron signature observed by ground-based telescopes, but at much higher precision and with additional chemical anomalies invisible from Earth, this could explain the extended analysis period. Artificial materials or engineered compounds would produce spectroscopic signatures requiring months of analysis for proper interpretation. NASA's Perseverance rover provides the most intriguing data comparison point. The rover's October 2 Skycam image showed 3i at LS as a distinct object against the Martian daytime sky. bright enough to register on instruments not designed for astronomical observation. By October 3rd, at closest approach, the object should have appeared significantly brighter and more detailed to the rover's cameras. Perseverance carries multiple high-resolution cameras, including the Mastcam Z system capable of detailed color imaging and the SuperCam instrument with laser-induced breakdown spectroscopy capabilities. While these instruments couldn't analyze 3I at LS composition directly due to distance limitations, they could document its appearance, structure, and behavior with much greater precision than the SkyCam. NASA's failure to release any Perseverance imagery from October 3rd suggests the rover captured something that contradicts the routine comet appearance shown in the October 2nd SkyCam image. The 24-hour evolution from relatively normal appearance to something requiring extended analysis implies rapid changes in 3I at LS characteristics as it approached closest distance to Mars. The thermal imaging capabilities available to multiple Mars missions provide another analytical avenue unavailable to ESA's primarily optical instruments. Both NASA and Chinese orbiters carry infrared sensors capable of measuring temperature distributions across 3I at LS surface and Coma structure. Thermal analysis could reveal whether 3I at LS displays heat signatures consistent with solar heating of natural materials, or whether unusual temperature patterns suggest internal heat sources, artificial materials with different thermal properties, or structured elements that don't radiate heat according to standard models. If thermal imaging revealed temperature distributions that don't match natural comet heating patterns, this would provide strong evidence for non-natural composition or internal structure. Such results would certainly justify extended analysis before public disclosure, particularly if they suggested technological components or engineered materials. The coordination of silence across agencies with such varied capabilities and political priorities suggests they all detected similar anomalies that require careful interpretation. The probability that all four agencies independently decided extended analysis was necessary for routine comet observations approaches zero. More likely, preliminary data sharing between agencies revealed consistent detection of unusual characteristics that merit coordinated response rather than independent publication. Such coordination typically occurs only for discoveries with implications extending beyond routine scientific research. The technical capabilities gap between ESA's instruments and those operated by NASA, China, and the UAE means their observations should provide exponentially more detailed information than ESA's preliminary results. Their continued silence while ESA publishes basic confirmation suggests the additional detail reveals complexity that can't be easily explained or safely disclosed. As we approach Perihelion, as public pressure for transparency intensifies, the agencies with the most capable instruments face increasingly difficult choices about information management. They can match ESA's disclosure level by releasing similarly basic results, or they can eventually reveal why their superior data required more cautious handling. The logical deduction from available information suggests they captured something far more complex than the slightly fuzzy white dot ESA described. Something that challenges conventional understanding enough to justify unprecedented coordination in information management across competing national space programs. The approaching perihelion passage creates a series of forced disclosure points that will make sustained information management increasingly difficult for space agencies maintaining silence about their 3I at LS observations. Understanding these timeline pressures reveals why ESA's October 7th disclosure may represent the opening move in a carefully orchestrated revelation sequence designed to prepare public expectations for more significant announcements. October 29th marks perihelion passage, when 3I at LS reaches closest approach to the Sun at 1.36 astronomical units. This event triggers maximum thermal loading on the object, potentially causing dramatic changes in appearance, structure, or behavior. If 3I at LS survives perihelion unchanged, displaying none of the dramatic outgassing increases expected for natural comets, this stability would strongly indicate unusual composition or internal structure. The geometry of perihelion passage places 3I at LS directly behind the Sun from Earth's perspective, making observation impossible for approximately 3 weeks. This observational blackout creates a natural boundary in the disclosure timeline, with pre-perihelion observations like ESA's representing before data that will be compared against post-perihelion observations to document any changes. November 18th represents the earliest date when 3I at LS might become observable again as it emerges from behind the Sun. Ground-based telescopes worldwide will immediately target the object, searching for changes in brightness, structure, or trajectory that might indicate unusual perihelion behavior. Any significant deviations from standard comet evolution will be apparent within days of re-emergence. This re-emergence date creates the first major forced disclosure point. If independent observers detect dramatic changes in 3I at LS characteristics, space agencies maintaining silence about their October observations will face immediate pressure to provide context and explanation based on their higher quality data. November 25th marks the beginning of the European Space Agency's JUICE spacecraft observation window. JUICE, currently en route to Jupiter, will observe 3I at LS from a unique vantage point, providing perspective unavailable from Earth. However, JUICE's communication timeline means observational data won't be transmitted to Earth until February 2026, creating a months-long information gap. The existence of JUICE observations that won't be available until February creates interesting strategic options for disclosure management. ESA could announce successful JUICE observations in November, while withholding results pending data transmission, maintaining public interest and pressure on other agencies without committing to specific revelations. December 15th represents a critical date for NASA's potential Juno mission redirection decision. If NASA chooses to redirect Juno for a March 2026 encounter with 3I at LS, that decision must be made before late December to allow sufficient trajectory modification time. The decision itself becomes a disclosure indicator. Choosing redirection suggests 3I at LS merits closer investigation, while declining suggests either routine characteristics or political constraints on extended observation. January 1st, 2026 marks the beginning of what might be called the second observation window. By this date, 3I at LS will be far enough from the Sun to allow comprehensive Earth-based telescopic observation. Ground-based instruments will have 6 weeks to conduct detailed analysis before 3I at LS potentially passes behind the Sun again, depending on observation geometry. This second window provides opportunities for international coordination on comprehensive observation campaigns that might reveal information not captured during the hurried October flyby period. It also represents the last realistic opportunity for detailed analysis before 3I at LS potentially becomes too distant for high-quality observation. February 1st represents the latest practical date for agencies to release October observation data, if they want it to inform the January-February observation window. Scientific value decreases dramatically if space agency data isn't available to guide ground-based observation strategies during this critical period. February 15th marks the expected transmission date for JUICE spacecraft data collected during November observations. ESA's release of this information could provide the first truly independent verification of 3I at LS post-perihelion characteristics, potentially confirming or contradicting whatever narrative has developed from ground-based observations. March 16th represents 3I at LS, closest approach to Jupiter at approximately 54 million kilometers. If NASA proceeds with Juno redirection, this date becomes the second major spacecraft encounter, potentially providing even higher resolution observations than the October Mars flyby. The timing creates another forced disclosure point. Juno's observations would be impossible to withhold given the mission's high public profile. April 1st, 2026 represents the practical end of detailed observation opportunities. 3I at LS moves beyond the effective range of most Earth-based telescopes and continues toward the outer solar system. After this date, the object becomes accessible only to the most powerful telescopes and spacecraft, effectively ending the period of intensive international observation. The pressure points created by this timeline extend beyond simple scientific curiosity. Each observation opportunity creates public expectations for data release, media coverage, and scientific interpretation. Agencies maintaining silence face escalating credibility costs as independent observations continue and alternative explanations gain public attention. Congressional oversight in the United States creates additional disclosure pressures. NASA operates under legislative mandate for scientific transparency and extended withholding of significant astronomical data without clear national security justification becomes politically unsustainable, particularly during election cycles when space policy faces increased scrutiny. International scientific collaboration agreements also create disclosure obligations. ESA, NASA, China, and the UAE participate in formal and informal data sharing arrangements that become strained when one party publishes results, while others maintain silence about related observations. The peer review publication process creates another timeline pressure. ESA's observations will eventually appear in scientific journals, creating permanent academic record of their findings and methodology. Other agencies face choices about supporting, contradicting, or ignoring these publications through their own academic contributions. Public interest and media attention create perhaps the strongest timeline pressures. Social media, amateur astronomy networks, and independent researchers continue generating analysis and speculation that space agencies cannot control. Extended silence, while independent investigation continues, risks loss of narrative control and credibility. The conspiracy theory implications also create timeline pressures. Extended silence from multiple agencies about the same observations inevitably generates speculation about cover-ups, hidden discoveries, or coordination to conceal significant findings. Such speculation becomes self-reinforcing and increasingly difficult to counteract the longer official silence continues. ESA's October 7th disclosure may represent strategic timing designed to begin controlled revelation while maintaining options for additional disclosures based on perihelion results and public reaction. Their establishment of baseline normal observations creates framework for either confirmation of routine characteristics or revelation of anomalies requiring more complex explanation. As we move through this revelation timeline, each passing date creates additional pressure for agencies maintaining silence to either justify their caution through eventual disclosure of extraordinary results, or face mounting credibility costs for withholding routine information that independent observers continue investigating. The question is whether the timeline pressures will force premature disclosure of incomplete analysis, or whether agencies will successfully manage revelation sequence to ensure public understanding and scientific credibility, while avoiding panic or misinterpretation of genuinely extraordinary discoveries. In the 72 hours following ESA's October 7th disclosure, a cascade of developments across the international space community has fundamentally altered the 3I@LS narrative. Leaked information, unofficial statements, and unprecedented coordination activities suggest we are witnessing the early stages of the most significant astronomical disclosure event in modern history. October 8th, 14:30 GMT. An anonymous source within NASA's Jet Propulsion Laboratory contacts multiple science journalists with claims that high-rise observations of 3I@LS show structural features inconsistent with natural comet formation. The source, identifying themselves only as JPL Observer, provides technical details about image processing techniques and specific anomalies that suggest inside knowledge of the actual observation data. The leaked information describes 3I@LS as displaying geometric regularity in its internal structure, with emission patterns that maintain consistent orientations despite rotational motion. These characteristics, according to the source, indicate possible engineered components that require extensive analysis before public release. While NASA officially refuses comment on leaked information, the technical accuracy of details provided by JPL Observer suggests access to genuine observation data. Independent verification of processing techniques and measurement methodologies confirms the source possesses knowledge available only to personnel directly involved in high-rise data analysis. October 8th, 22:15 GMT, the Chinese National Space Administration issues an unusual statement through their English-language social media channels. Tianwen-1 observations of interstellar object 3I@LS are undergoing comprehensive analysis in coordination with international partners. Results will be shared when analysis is complete. This represents the first official acknowledgement from CNSA that Tianwen-1 attempted 3I@LS observations. More significantly, the reference to coordination with international partners confirms multi-agency communication about results, contradicting earlier assumptions about independent analysis by competing space programs. The timing of CNSA's statement, less than 24 hours after the JPL leak, suggests reactive communication management rather than planned disclosure. Chinese space officials rarely acknowledge international coordination, making this admission a significant departure from normal operational security. October 9th, 8 o'clock GMT. Dr. Colin Wilson, ESA's project scientist quoted in the original October 7th disclosure, when pressed about spectroscopic uncertainty, Wilson provides clarification that generates more questions than answers. Our instruments successfully obtained spectroscopic data during the flyby period. The uncertainty relates to interpretation of unusual signatures that don't match standard comet chemistry models. We're conducting additional analysis to determine whether these signatures represent exotic natural chemistry or require alternative explanations. This statement represents a significant evolution from ESA's original claim of uncertainty about detection itself. Wilson's confirmation of successful spectroscopic observation, combined with acknowledgement of unusual signatures, suggests ESA possesses chemical analysis data that challenges conventional understanding. October 9, 1645 GMT. Multiple sources within the European astronomical community report receiving informal communications from ESA officials requesting discretion about preliminary analysis of 3I@LS observations. These communications, described as guidance rather than official restrictions, suggest ESA is managing information flow beyond their formal disclosure channels. The informal communication network within European astronomy includes researchers at major observatories, university departments, and international collaboration projects. ESA's outreach to this community indicates concern about uncontrolled information distribution and potential misinterpretation of technical details. October 10th, 12:30 GMT, the United Arab Emirates Space Agency breaks its silence with a carefully worded statement through their official website. Hope Orbiter conducted successful observations of 3I@LS during the October flyby period. Spectroscopic data analysis is ongoing in collaboration with international partners. Results will contribute to global understanding of interstellar object characteristics. The UAE's statement follows the same pattern as China's acknowledgement of international coordination, confirming multi-agency communication while maintaining discretion about specific results. Their emphasis on global understanding suggests discoveries with implications extending beyond routine scientific research. October 10th, 1820 GMT, social media accounts associated with several NASA employees begin sharing cryptic messages suggesting significant discoveries require careful presentation. While avoiding specific technical details, these posts reference paradigm-shifting observations and responsible disclosure of extraordinary findings. The coordinated nature of these social media activities suggests either organized information campaign or spontaneous community response to internal NASA discussions about 3I@LS results. The emphasis on responsible disclosure implies results that could be misinterpreted or cause public concern if presented without proper context. October 11th, 9:15 GMT, ESA issues a supplementary statement, clarifying their October 7th disclosure. Additional analysis of Mars Express imagery has revealed previously undetected features in 3I@LS observations. These findings are being evaluated in coordination with international partners to ensure comprehensive understanding before detailed publication. This represents the first official acknowledgement that ESA possesses more detailed information than their initial disclosure suggested. The reference to previously undetected features confirms that enhanced analysis has revealed additional complexity not emphasized in their original statements. October 11th, 1440 GMT, multiple European observatories report receiving requests from ESA for coordination of public communications regarding 3I@LS research. These requests, described as recommendations rather than requirements, suggest ESA is attempting to coordinate messaging across the broader European astronomical community. The coordination requests specifically mention concerns about maintaining scientific credibility and avoiding premature conclusions about 3I@LS characteristics. This language suggests ESA recognizes their disclosures have generated speculation that might complicate future revelations. October 11th, 2030 GMT. Anonymous sources within the International Astronomical Union confirm that IAU Working Group on Nomenclature is conducting emergency consultations about 3I@LS classification. The working group, responsible for astronomical object naming and classification, typically operates on monthly schedules for routine decisions. The emergency consultation process suggests 3I@LS may require classification categories that don't exist within current IAU frameworks. If observations indicate artificial origin or unusual physical properties, new classification systems might be necessary to properly categorize the object. October 12th, 11 o'clock GMT, NASA issues its first official statement about 3I@LS, since the government shutdown began. NASA missions have successfully observed interstellar object 3I at LS during its passage through the inner solar system. Analysis of collected data is ongoing. Despite current operational constraints, results will be shared when analysis is complete. The statement, while minimal, represents a significant development given NASA's complete silence since October 3rd. The reference to operational constraints acknowledges the government shutdown while confirming that analysis continues despite bureaucratic limitations. October 12, 1625 GMT. The Committee on Space Research (CICOSPA) announces an extraordinary session scheduled for November 15th to discuss recent observations of interstellar phenomena. The session, open only to COSPA member representatives, will address coordination of international response to significant astronomical discoveries. COSPA's extraordinary session announcement confirms that 3I at LS observations are being discussed at the highest levels of international space science coordination. The restricted attendance and emphasis on significant discoveries suggests results that require careful international consultation. These rapid developments following ESA's initial disclosure reveal a global space community grappling with discoveries that extend far beyond routine comet observations. The coordination activities, unofficial communications, and evolving statements suggest agencies are managing information about findings that could fundamentally alter our understanding of 3I at LS' true nature. The pattern of leaks, official acknowledgements, and coordination requests indicates we are witnessing controlled disclosure of information too significant to withhold indefinitely, but too complex to release without careful preparation and international consultation. As pressure continues building for comprehensive disclosure, as Perihelion approaches, as independent analysis continues, the space community faces unprecedented challenges in managing public understanding of discoveries that may represent the most important astronomical observations in human history. ESA's strategic disclosure and the subsequent cascade of coordinated agency responses represent far more than routine scientific transparency about an unusual comet. We are witnessing the early stages of humanity's first managed encounter with a phenomenon that challenges our fundamental understanding of our place in the universe, and the implications extend far beyond astronomy into questions of human readiness, institutional credibility, and species-level decision-making. The coordination patterns emerging across space agencies, astronomical institutions, and international organizations reveal a level of information management unprecedented in modern scientific history. When competing national space programs coordinate silence, when independent researchers receive informal guidance about discretion, when international bodies convene emergency sessions, we are observing institutional recognition that 3I at LS represents something requiring careful societal preparation rather than routine scientific publication. This institutional behavior suggests discoveries significant enough to warrant extraordinary caution in disclosure. If 3I at LS displayed clearly natural characteristics, if its anomalies could be explained through conventional physics and chemistry, there would be no need for multi-agency coordination, no requirement for international consultation, no concerns about public misinterpretation or social disruption. The agencies involved in these coordination efforts represent humanity's most advanced technological capabilities and scientific expertise. Their collective assessment that 3I at LS merits unprecedented information management indicates discoveries that transcend routine scientific research and enter territory with profound implications for human civilization. Consider what level of discovery would justify such coordination. Detection of clearly artificial materials would represent first confirmed evidence of extraterrestrial technology. Discovery of impossible physics would revolutionize our understanding of natural law. Confirmation of intentional targeting toward our solar system would indicate active interest in humanity by intelligence capable of interstellar travel. Any of these discoveries would warrant careful presentation to avoid panic, misinterpretation, or social disruption. All would require international consultation about appropriate response strategies, disclosure timing, and long-term implications for human society. The observed coordination patterns suggest at least one, possibly multiple, discoveries of this magnitude. The timing of ESA's disclosure, followed by controlled revelation of additional information through leaks, official statements, and international coordination activities, indicates a managed disclosure strategy designed to gradually prepare public consciousness for revolutionary discoveries. This approach suggests recognition that humanity lacks psychological, social, and institutional frameworks for processing genuinely paradigm-shifting information. The scientific community's response reveals deep divisions about appropriate levels of transparency versus public readiness. Traditional scientific ethics mandate open publication of research results, peer review processes, and unrestricted access to data. The apparent coordination to control information distribution violates these principles unless justified by discoveries with implications extending far beyond academic research. The institutional credibility crisis emerging from extended silence while independent researchers continue investigation represents a calculated risk. Space agencies are accepting damage to their reputations for scientific transparency in exchange for control over disclosure, timing, and presentation. This trade-off suggests they believe uncontrolled revelation would cause greater harm than temporary loss of credibility. The global nature of coordination indicates recognition that 3I at LS implications extend beyond national interests to species-level concerns. When American, Chinese, European, and Arab space programs coordinate information management despite political tensions and competitive pressures, they are acknowledging discoveries that transcend geopolitical boundaries. This coordination also reveals existing communication channels and decision-making frameworks for managing discoveries with global implications. The rapid emergence of coordinated responses suggests pre-existing protocols, possibly developed following Oumuamua observations, for handling potentially extraordinary astronomical discoveries. The role of international organizations, particularly the International Astronomical Union and Committee on Space Research, indicates institutional recognition that traditional scientific publication processes may be inadequate for managing discovery disclosure, with profound social implications. Emergency sessions and extraordinary consultations suggest adaptation of academic institutions to handle information too significant for routine publication. The amateur astronomy community's continued independent investigation creates pressure that professional institutions cannot control. Distributed observation networks, social media communication, and independent analysis capabilities mean that information management strategies face constant challenge from sources outside institutional control. This dynamic creates timeline pressure for official disclosure before independent researchers reach conclusions that might be presented without appropriate context or preparation. The balance between institutional control and independent discovery represents a fundamental challenge for managing societal preparation for extraordinary revelations. The psychological implications for human civilization extend far beyond the specific nature of 3I at LS discoveries. The revelation that our institutions possess capabilities for coordinated information management about discoveries of cosmic significance alters public understanding of governmental transparency, scientific openness, and democratic access to information about phenomena affecting all humanity. If 3I at LS represents first confirmed evidence of extraterrestrial intelligence, humanity faces immediate questions about contact protocols, response strategies, and long-term implications for human society. If it represents advanced physics beyond current understanding, we face questions about technological development, scientific paradigm shifts, and potential applications of impossible technologies. Either discovery would catalyze transformation of human perspective about our cosmic significance, technological capabilities, and future development potential. The institutional coordination we observe suggests recognition that such transformation requires careful management to avoid social disruption while enabling appropriate adaptation. The timeline approaching perihelion creates forced decision points that will determine whether humanity demonstrates readiness for cosmic citizenship or reveals institutional and social inadequacies in processing interfusional and social inadequacies in processing revolutionary information. The success or failure of managed disclosure strategies will establish precedents for handling future discoveries of similar magnitude. The international cooperation emerging around 3I at LS coordination provides hopeful evidence that humanity can transcend political divisions when confronted with phenomena of species-level significance. The collaboration between competing space programs suggests potential for broader cooperation in addressing challenges that affect all human civilization. Conversely, the apparent need for information management suggests institutional assessment that humanity lacks sufficient maturity, wisdom, or stability to process extraordinary discoveries without risk of panic, social disruption, or destructive response. This assessment, if accurate, indicates fundamental challenges in human social evolution that must be addressed before we can safely engage with cosmic phenomena beyond our current understanding. As we approach perihelion, as disclosure pressures intensify, as independent investigation continues, humanity faces a test of our readiness to learn truths about our universe that may fundamentally alter our self-understanding, our technological capabilities, and our future development as a species. The question is not simply what 3I at LS represents, but whether humanity demonstrates sufficient wisdom, cooperation, and emotional maturity to process whatever truth emerges from this unprecedented encounter with the unknown. Our response to 3I at LS may determine whether we prove ready for cosmic citizenship, or reveal that we remain too primitive, too divided, and too reactive to safely engage with phenomena that transcend the comfortable boundaries of our current understanding. The universe is watching, and our institutional coordination, public reaction, and ultimate response will establish humanity's reputation in whatever cosmic community may be observing our first encounter with genuinely extraordinary phenomena.